That's a perfect polar region, isn't it? In polar, we would say that that's the set of points r and theta, right? Where it doesn't matter what order you do this in. Let's go theta first. Theta is between 0 to all the way around, right? 2 pi. And your radius is between 0 to 2, right? 0 to 2. 0 to 2. Oh, I forgot my brace at the end here. So you may see me like in my homework solution videos, or like maybe as we proceed through this. I'm going to stop doing all this for polar. I'm just going to write theta between 0 and 2 pi. And then I'll say r is between 0 and 2. I'm not going to say, hey, we're in polar. It's understood we're in polar, and here are our restrictions, right? OK. All right, awesome. So we have the polar region on the ground. It happens to be a polar rectangle. That's awesome. And so now what I'm going to do is I'm going to set up the double integral. My double integral is going to go over that region r. It's going to be the function, right, f of xy. Well, what's f of xy for us? 4 minus x squared minus y squared, right? And then do that with respect to area. But polar is what works here, right? Polar is what works. So when we do polar here, when we go to polar, we're going to do double integral over r, but now this becomes 4, okay, minus x squared minus y squared. So remember, x is what? R cosine theta, and y is r sine theta, right? However, back when I first introduced the idea of polar, there was a couple of formulas I gave you. Right here, Cartesian and polar relationships. Yes, x is r cosine theta, y is r sine theta, but remember this one. Oh, I covered it up. What? X squared plus y squared equals r squared, right? So anytime we ever see x squared plus y squared, that's equal to r squared. Anytime we see x squared plus y squared, that's equal to r squared. Do you all see this right here can be rewritten as 4 minus, bring out the minus from these, x squared plus y squared? Isn't that the same thing? So this is really just 4 minus r squared dA. And now I'm going to go and replace my dA with r dr d theta or d theta dr. It's totally up to me because those are constants. Y'all understand? Pretty cool, right? All right, so this now becomes, all right, double integral. Let me do this first. 4 minus r squared, and now I have to replace the dA with what? R, right? You need the r in here. And then, do y'all care? Nope. We'll go dr d theta. How about that? Because I have r's in there, right? And then now I can put my limits of integration. Theta is the outer one, 0 to 2 pi, and r is the inner one, 0 to 2. One more thing, and then I'll say I'm done with this problem. Yeah, get the r distributed through. So 0 to 2 pi, 0 to 2, 4r minus r cubed dr d theta. And I think that would be pretty straightforward, wouldn't it? So I want to show you something. We're done. I want to show you something that we can also do here. This was a special property from way back when we first started talking about integrals, double integrals. That wasn't way back, a week or two ago. Notice that we have two variables, r and theta, right? And notice that this expression has no thetas in it. So it's like the thetas and the r's are separated from one another. So you are allowed to do this if you want to. Now, I personally don't do this, but I want to show you the property. What I can do is I can separate this into two integrals being multiplied. One of them is with respect to r, the other one's with respect to theta. That's only because there's no thetas and r's mixed together. It's not like cosine of r theta or something like that. So I can do my integral with respect to r first, right here. And what's my restriction, 0 to 2? Whatever that answer is, I multiply it, not add, the integral from 0 to 2 pi of what do you think here? 1 d theta. 1 d theta. Now, again, you don't have to do this. You could just do what I did in the previous example, right? First do this with respect to r, and then after that, do it with respect to theta. You'll get the same answer. Okay, I'm going to stop, though. Can I move on? Yes?
So this was like a complete circle, so no gaps in between. Not that I want to see it done, but Cartesian, would that be possible with this question?
You mean to force ourselves to do Cartesian?
Yeah.
Yeah.
Would it be simpler? Well, not simpler. Would it be, could that have been done?
If we were absolutely, like, what's the word I'm looking for? Stubborn?
Yeah.
And we didn't want to do polar here, the region still looks like this on the ground, right? Wait, was it a full circle?
Yeah.
It was a full circle. So what I would have to do is I have to break it up into two things. I would have to do an integral over that region first, and then I do another integral over this region, right? And remembering that this right here, what was the radius on the circle? It was 2, right? Yeah. So this would be y equals the square root of 4 minus x squared, and then the bottom one would be y equals negative square root of 4 minus x squared. So that draws me the full circle, the top and the bottom. So now what I need to do is this. For this region right here, let's call that R1, R2, I would have to do, yeah, 2 doubles. So I would, if I wanted to know the double integral over the region, the whole region, let's call the whole region R, of this thing, 4 minus x squared minus y squared with respect to area, if that's what I was trying to do, right, I would have to break this into, first the double integral over R1 of 4 minus x squared minus y squared dA, plus now the double integral over R2 of 4 minus x squared minus y squared dA, right? And then on this one, double integral, okay, now I'm on R1. So this is 4 minus x squared minus y squared. But now I'm going to go change dA to, well, what type region is this? My x's are between two constants, my y's are between two functions, right? Yeah. So my x's are between where and where? Negative 2 to 2. So my x's are between negative 2 to 2. And my y's are between 0 to that curve. Yeah. So 0 to the square root of 4 minus x squared minus, no, just 4 minus x squared, sorry. Right? Yeah. And then now it's dy dx. So I have to do that integral. So I have to integrate this with respect to y first. Yeah. Once I get that, I replace y with this and this. Figure out what that is, and then integrate that with respect to x, and then plug in negative 2 and 2. Okay. I'm only halfway. Then I have to plus now this one, right? Yeah. So this one, and now I'm down here, right? So your restrictions are still between negative 2 and 2. Restrictions on y now are between negative root 4 minus x squared. I keep on doing one, do y squared. 4 minus x squared to 0, right? So that's from here to here. And then 4 minus x squared minus y squared dy dx. Okay. I'm arguing the polar was much better, yes? Yes. Yeah. But yes, you could, in this particular problem, you could force Cartesian. Okay. You could forcibly make it happen. Yes? What's up?
I'm a little bit confused.
Okay.
Just because I think one of the homework problems has to do this with Cartesian.
Okay.
Not the exact same way, but it's still like on the ground, it was a circle.
Okay.
And I kind of set it up going from negative 2 to positive 2. And then from negative square root of 4.
You can do it. You can do it that way too. If you, if you could do one double integral instead of 2, if you realize that, you know what, you could define this whole region, x is between negative 2 to 2, and then you could go from the bottom surface to the top. So just replace this with negative root 4 minus x squared and just do one integral. You could. Okay. That'd probably be more efficient, I would say. But I guess when I was looking, yeah, I think that's more efficient, but it's still going to get you the same place, right? Yeah. So.
Okay.
All right, shall we move on? Do you want to see it now? Yeah. There's the surface, the paraboloid we found. Oh, you know what the solid looked like. It was kind of boring, right? Okay. All right, now we need to change gears. When we were doing double integrals, right, when we first started this topic, right, when we first started it, we said, okay, we're going to do double integrals over rectangles, right, in Cartesian, rectangles. Then after rectangles, we said, well, wait a minute, it's not always going to be a rectangle. And then we gave you a couple of other reasons. We classified them as type 1 and type 2, right? Type 1, the x was between two constants, and the y was between two functions of x. And then type 2, the y's were between two constants, and the x's were between two functions of y. That was type 2. Well, guess what? We have that same idea in polar, right? Instead of both your r and your theta being stuck between constants, you could have your theta between two constants and your radius between two functions of theta, or you could have your radiuses stuck between two constants and your theta's stuck between two functions of r, right? So I mean, but we will only deal with one type of those, okay? We'll only deal with one kind, all right? I'm going to jump to that. Where is it? Okay, so this is it. See, instead of having your your theta between two constants and your radius between two constants, these radii might actually fluctuate as functions of theta. And in that case that you have that, your domain or your region will be the polar points where your theta is between two constants and your radius is between two functions of theta. And now you don't have a choice in changing the order. You must do this alpha beta on the outside with respect to theta, and then the inside has to be your limit, your function limits on the radius, right? And then this is still converted, and you still have the r in there. So that's just to show you. I mean, it can happen. I'm going to do an example, but what if we have two surfaces and we want to find the volume between them? We did that already before. If I give you two surfaces, want to find the volume between them, you're just going to do a double integral. You're going to take the top surface and subtract the bottom one. Top surface, subtract the bottom, right? That's something we've seen before. But we can do this in polar as well, right? So if your region on the ground is polar and you want to find the volume of this solid, well, you need to know the top surface and bottom surface, and you'll just subtract those two. So this is a good example of that. Find the volume of the solid below x squared plus y squared plus z squared equals 1. Now, I should have said there, find the volume of the solid inside that, because what is x squared plus y squared plus z squared? Equals 1. Sphere of radius 1, right? It's a sphere. So when I say below, that doesn't make a lot of sense. I should have said inside, right? Find the volume of the solid inside that. Let me change it. Inside. And above, I'll leave. Above this cone. Shall we do Desmos again? Just so we can see it. X squared plus y squared plus z squared equals 1. And then the other one was square root. What was it? Yeah, x squared plus y squared. I forgot z here. Oh, it doesn't even need it. There we go. So there they are. We want inside the ball, but above the cone. When I say above, y'all understand what I mean by above? Yeah? All right. There is a way to change your opacity, I believe. Let me see. Translucent surfaces. There we go. That's all you can do here. You can see through a little bit, right? So we're trying to find the volume of that thing in there. Looks like a what? What is the thing we're trying to find the volume of? What does that look like, that shape? To me, it looks like a little snow cone.
Yeah.
Looks like a snow cone, right? Okay, so that's Desmos. Let's see what I have. There we go. You don't see that? Cone, ball, but I can bring out the sphere, I can bring out the cone, and just show you the solid. There we go. That's what we're looking at. Okay, so if you look at that, you can see that the top surface is the sphere, right? And the bottom surface is the cone. But what's the region on the ground? See, you need the region on the ground. Wouldn't that be if you like projected this shadow down onto the ground? That's your R on the ground, right? So you need to know what that is. So what is that radius? Let's figure it out, because that radius is not the radius of the sphere. It's not, right? Where's the sphere? The sphere is that, right?
Oh.
You see that?
Yeah.
The cone is like that. So your shadow on the ground, which is the region you're integrating over, is not, well, it's not 1. So how are you going to figure it out? Let me put the two surfaces here. Right. So how do you figure out? I mean, do we agree that that should be a circle on the ground?
Yes.
It's just the question is, what's the radius?
Would you solve for Z on the top of it and?
Yeah, you set them equal to each other, or you can just replace Z with this in there, right? That'd be the same as setting them equal to one another. So why don't we do that? Let's just replace this Z right there. Let's replace that with this. And then when you square it, it just becomes x squared plus y squared. That's this. Plus that squared, x squared plus y squared equals 1. Okay, this is 2x squared plus 2y squared equals 1, which means x squared plus y squared equals a half, right? The radius is square root of 1 over 2, or however you want to write it. Yeah, it's square root of 1/2, which is same as 1 over root 2, or you could even do root 2 over 2, whoever you want. That's your radius, right? Okay. Any questions before I start setting this thing up? All right, it's definitely a polar region. Let's go ahead and draw this polar region. Polar, right. It's got a radius of 1 over root 2. 1 over root 2 is that radius. So in terms of polar, my theta is between two constants, my r is between two constants in this problem, right? Theta is between 0 and 2 pi. And my radius is between 0 to 1 over root 2, or however you want to write that. Right? That's my polar. It's a polar rectangle. It's still a polar rectangle. All right, so we've got that. And now I need my double integral, right? I need my double integral. What's that? Yeah, the dr d theta is not going to matter that order. We just need to make sure we put the r in there, but we need the dr d theta. We can pick that. The issue though here is we've got to get the top surface and bottom surface, right? So top surface is the part of the sphere. Here's your sphere equation, right? Right now that's not a surface yet, right? Because you have to solve that for z for it to be a function of x and y, right? So let me start setting this up. We're going to call this region, let's call it D, because in my notes I called it D. I've called them both R and D, so I want to just kind of switch it up. R for region, D for domain, okay? We're trying to do the double integral over D, okay? And then I'm going to do the top surface. That's this solves for Z, which would be?
Plus or minus?
Plus or minus, well, which one is it? It can't do both. Because when you solve that for Z, you get plus or minus. So is this top part of the sphere the plus or the minus?
Oh, the plus.
It's the plus, and then the bottom part is the minus. So I'm only going to do the plus. Square root of 1 minus what? X squared minus y squared. Ooh. Ooh, okay. And then that's the top surface minus what? The bottom surface, which is this square root of x squared plus y squared, right? I want to do that dA, right? That's what I'm trying to do. Any questions on where I got any of that? Now's the time. Come on. Questions? No? No? Everyone's clear on that? Okay, I haven't done any polar conversion yet. I'm about to do polar conversion. So when I do the polar conversion, I want to get all this stuff off the screen. It's just in my way. So when I do this polar conversion, I'm gonna swing this up here. So I'm going to polar here. Double integral still over d. All right, this is going to become nice, right? Because I can factor out the -1 again, right? Factor out the, I'm sorry, negative or -1 from here. So it'll be 1 minus the square root of 1 minus what? The x squared plus y squared becomes r squared. Beautiful. And then I'll have minus, now this is just r, right? That's just r, because x squared plus y squared is r squared, and then the square root of r squared is r. And then, yeah, we'll leave it dA. That's okay. I'll do dA still. And now I'll go ahead and get my double integral. Let's get our limits of integration. Let's stick the r in there, right? We need that r to come in. Okay, here comes the r. And yeah, we'll still stick with dr d theta. So r, radius, is the inside one, 0 to 1 over root 2, and then the outer one, 0 to 2 pi. There we go. That is the volume, whatever that is. Distribute the r through. Ooh, distributing the r makes things nice, right? Because if I try to integrate this right here, I'd need to use either a formula or trig sub, trigonometric substitution. But by putting the r out in front of it, now you can just use a basic u sub, because the derivative of the inside would be, it'd be off by a constant. So either way, I think I just give the answer here, do I? No. Do we want to know the answer? Let's just get it. I'm going to get a numerical answer. So I'll go use the computer again. Let's go to, what do you want? Wolfram? I still use Wolfram. Am I out of touch? Is Wolfram still a place to go, or is it all Symbolab now? Or is there something else? Wolfram. Okay, I'm going to do double integral. So I do an integral. Inside that, I do another integral. So 0 to 2 pi. And then I can go 0 to 1 over square root of 2. See how it handles this. And then I'm doing, yeah, I'll do it that way. I'll do square root of 1 minus r squared. And then that minus r, right? And then I needed times another r. And then drd. I'm going to use t for theta. And then let's just see how it handles that. .61343. There we go. Okay. We already saw geometrically what we found the volume of. All right. All right. So this is what I was just talking about. If you have a double integral that's not a rectangle, right? Not polar rectangle, you have something else where your theta, yeah, your theta might be between two constants, but your radius is not between two constants. That's something we would like to be able to handle. And I'm going to show you an example. I'm going to go get some water. I want you to read that. Think about it. You need to see the picture. It's a little too big. Can you all see this sphere? That green is like a drill bit that's drilled through. So just think about it for a second and while I get a drink, because I'm curious what your thoughts are on this when I come back. So what are you thinking?
Well, the sphere radius 3 would just be x squared plus y squared plus z squared equals 3. No.
9.
Yeah.
9. Okay, so right now you're just saying, okay, well, we know this much. We know that that's the equation of that sphere. I agree.
Would the cylinder be the x squared plus y squared equals 1?
X squared plus y squared equal. Is that? Well, is that?
Because z is 3.
Z is free. So back up for a second. Let's make sure we all understand what's going on. We're drilling out that piece, right?
Yeah.
And when we drill that out, we get this. And we want the volume of this. This problem would actually be pretty simple if that drill was going right through the center. If it went right through the center, then this would be an easier problem. But it's not through the center. It would still be a little hard, but it would be easier than what we're dealing with here because it's not through the center of the sphere, right? So when how are we going to do this? Let's talk about the part that actually got drilled out. Like, okay, there's my drill bit, right? When I drill out, that's the part that gets drilled out. Do you all see that? The drill bit comes in, right? The drill bit comes in, drills out that section right there. So if you look at that solid right there, right? From the top, you see that it's like on the ground, it's a circle, but it's not centered, right? That yellow part, it's not centered, but it is a circle. And this piece here it's like a cylinder, but the top is not flat, right? The top is actually a little curved, and the bottom is a little curved. Do you all agree that if we could figure out the volume of that yellow piece, right? Then we just subtract it from the volume of a sphere. We already know the volume of a sphere is 4/3 pi r cubed. That's just a generic formula. I actually proved that formula in my Cal 2 class today. We proved that formula is true by just wrapping a curve around the x-axis and find the volume. So if we can all settle on the idea that the volume of the entire ball is 4/3 pi r cubed with r being 3, then if we can just subtract the yellow, we'll have it, yes? So we got to find the volume of that yellow. We got to find the volume of the yellow. So if we want to try and find the volume of that yellow, why don't we make the problem even easier because of symmetry, and let's just find the volume of half of it and then double that. Because that piece right there, right, we've got a, can you all see it? We've got, the top is a little curved piece. The bottom this time is flat, right? That is flat. So if I can find the volume of that red, I'll just double it. So do you have a top surface? What's the top surface of this solid? That, right? Solved for z and then taking only the positive root. And then what's the bottom? Well, just the xy plane. So we're actually back to just going from there all the way down to the xy plane, so we don't need to subtract anything. Yeah? Questions?
What's that region?
The region on the ground's the problem, right?
Yeah.
So the way that I said this is that the sphere is a radius 3, cylinder has a radius of 1, and it's drilled out as shown. So when we look at it from the top, right, I'm telling you that this circle has a radius of 1, and it's like tangent to the axis. I mean, it's like the drill bit. Instead of going right down the center of the ball, we put it so that the drill bit was like tangent to the z-axis and just drilled down. So we just have to figure out how we want to define that region. So let me do it this way. I'm going to give myself some space again. All right. So if I look at this region on the ground, I'm trying to figure out what it is. I'll go back to R. I can orient this however I want. Okay, that red piece, the shadow of it on the ground, I'm going to choose to orient it like this. Okay? I could have done it any way I wanted. I mean, I could have done this if I wanted to. Doesn't matter how it is relative to the z, like the z-axis. But I think it makes most sense to put it just kind of offset. Does that, like this is symmetric. There and there is the same. But I could have done it this way. This would be harder. Okay. Well, you know this has a radius of 1, right? So if I do it that way, can you tell me what the center of this sphere is? Well, what is it as a point? No, the radius is 1. Be careful. The radius is 1.
1, 0.
So that has a point. That point is the point 1, 0. Y'all agree? It's point 1, 0. Okay? All right. You know the center of a circle, don't you? And you know its radius. So can you come up with the equation of that circle then? Remember the formula, x minus h squared plus y minus k squared equals r squared is a generic formula for the equation of a circle in two-dimensional space. So for us, it's going to be x minus 1 squared plus y squared equals r squared.